All right, I'm going to start by showing how to do the chi-square test or how to use this chart here. All right, so I'm going to come back to this table in a bit. Right. Let me explain how to use it and then do a quick example. So this will come under genetics. So when you're doing experiments, so if you remember with like the dihybrid cross, right? If you cross two heterozygotes offsprings in terms of phenotypic ratio, you expect a 9 to 3 to 3 to 1. So based on Mendel's laws, right? If you do a certain cross, you will have a certain expectations of the outcome. The purpose of doing a chi-square test, you will have your expectations, and then when you do an experiment, you're going to get some results. What you want to know if those results that you get, if the difference, so what will you say? The difference between our observed, there will be no difference between our observations and our expectations. But if there is any difference, it will be due to chance. So this table here and our chi-squared value, we are going to determine if any differences between our observed results and our expectations is due to chance. All right. So that is the purpose of this. When we do a cross, we have an expectations. We're going to get results. We want to know if it is due to chance or not. All right. How do we use this table? The first column here is the degree of freedom. So you have 1, 2, 3, 4. I will show you how to get the degree of freedom. Just a second. All right, so this is their degree of freedom. For biology, these readings up here, the probabilities, we use 0.5. Sorry, this is 0.05. So if this should come on the exam, do not worry about these other readings. So we are interested in degrees of freedom and this column here with the probability 0.05. So what you're going to do, let us say your degree of freedom is 2. You're going to find where it intersects the 0.05. So you have a degree of freedom of 2 and you have your probability of 0.5. You're going to look at this value here. And based on what we calculated, we're going to see if it is greater than the 5.99 or less. So this number that intersects with where the degree of freedom and the probability meets, that is our critical value. All right. So you find your degree of freedom and you match it with the 0.05. So let us do a quick example. By the way, before I move, any question? All right.
Yes, sir. So the degree, the way board gone.
Me clear it already.
All right, no bother.
Yeah, continue.
So the degree of freedom for the two would that be 5.59?
Right. So we're going to use this critical value of 5.99.
Okay.
Yeah. All right. So let's show you how it works. Go back to the whiteboard. All right. So everybody is supposed to know the experiment with Mendel and the pea plant, right? And what are the phenotypes with the dihybrid cross with the pea plant? Ronan yellow, wrinkled green, that experiment. One second to just connect this. All right, I'm just going to use the, all right, so which one is this? Do you know how to do a null hypothesis?
No, sir.
All right, so your null hypothesis with, all right, hold on. So let us say you have a plant, right? Let's use B for blue flowers. Move quickly. And small b for white flowers. Right? And we cross two heterozygous offsprings. So big B, little b, big B, little b. So in this box it would be big B, this box, big B, little b, big B, little b. What is the phenotypic ratio? How many blue flowers will we have?
3 blue flowers to 1 white.
Okay. Yes, so the phenotypic ratio is 3 to 1. What would be the genotypic ratio? You start with your homozygous dominant one. So how many would be homozygous dominant?
1. Wait.
1. Then you do the heterozygous. How many would be heterozygous?
2. 2.
Right. And how many would be homozygous recessive?
1.
Yeah. So for the chi-square test and null hypothesis that we're going to do, we're not interested in the genotypic ratio. We're interested in the phenotypic ratio. So what is this phenotypic ratio saying? If we have 4, let's start out with, if you have 4 flowers, right? Out of the 4, how many should be blue?
3 would be blue, 1 will be white.
Out of 4 flowers, 3 blue and 1 white. In terms of percentage, what percentage should be blue?
So you're going to say 3 over 4 times.
75.
Right. So 3 over 4, which is equal to 75%. So 75% of the flowers should be blue. So whenever you do a heterozygous cross for monohybrid, 75% should have the dominant trait, and 25% should have the recessive trait, which is white. So 25%. Go
When you
ahead.
do a monohybrid cross, 75% dominant, 25% recessive, that's what you said?
For a two heterozygous cross. There's not any cross, it has to be 2 heterozygous offsprings. well, will be offspring, parents. So when you cross two heterozygous parents, for the phenotype, 75% should be of the dominant trait, and 25% is of the recessive trait. So question, if you have 50 flowers, right? How many should be blue? So if you cross the offsprings, two heterozygous ones, right? Not offspring, parents. And you get 50 offsprings. How many of it should be blue and how many should be white?
49 blue, 1 white.
No, man. Look at the
Wait.
percentage.
It would be 12.5.
So you get 12.5 for the
What are
white?
the 50?
Yeah.
Yeah, it would have been 12.5 and
All right, so run it. All right, so 37 blue and 12. But run it off to 13 would be white.
So I don't round off the blue too because it's 37.5.
Well, one would have a run off. Kind of have half of.
Oh, all right, yeah.
Over there. So if we're doing an experiment, right? Before we do the experiment, 37 of the flowers is expected to be blue. So this is our expectations. 37 would be blue and 13 will be white. All right, that is our expectation. Let us say we do the experiment now. And you get, let us say you get 25, not 25. Let's say you get 31, that is white, and 19, because it's 50 in total, 19, that is 31 blue and 19 white. So before we start our experiment, we would have a hypothesis, null hypothesis. What we're going to say, so essentially you're saying there will be no significant difference between observed and the expected. So there will be no significant difference between observed and expected. So at the end of the experiment, we are going to either accept the null hypothesis or reject it. So how are we going to do that? We have to do a little calculation. So I need to clear some of the word. Give me a second. All right, yeah, sorry about that. All right, so, right, the chi-squared value, if we want to work it out, this symbol here, anybody know what this symbol means?
Sum of.
All right, observed minus. So O is for observed, E is for expected. All right, divided by E. All right, in the interest of time, I'm just going to use some data from this study guide. All right, so, all right, let's put my rationale. All right, so I should probably screenshot it and put it. Give me a second. Let me just. Give me a second. Let's do this. I'm just emailing the page so I can bring it up on this. Zoom out a bit. All right, ready again. All right, so everybody can see the table now, right?
Yes, sir.
All right, so this is the formula. So that means sum of observed minus expected. So this one is a dihybrid cross. Right, so for in this particular example, right, they were describing tomato plants. So remember, in dihybrid cross, we are doing two types of traits. So in this one, it was purple cut. Yeah, so these are the two traits. Their expectation was a 1-to-1-to-1 ratio. And their null hypothesis, you're always going to say there is no significant difference between the observed and the expected. Yes, I'm going to do genetic engineering shortly. What you're going to do, based on the data provided, we are going to work out the observed minus expected. So here you have the category. The observed was 70. The expected was 81. So if it's a 1-to-1-to-1-to-1 ratio, then they all have to be the same. So the total amount of plants is 324. And if it is a 1-to-1-to-1-to-1 ratio, they all have to be the same. In the monohybrid cross we did, with the 3-to-1 ratio, so apply ratio, one number you get. So in this case, it was 324 plants. So since the ratio is 1-to-1-to-1, everything has to be equal. This is our expectation. Now, for the first plant, this is what we observed. as it says, observed minus expected, you square it. So it would be 70, take away 81, which you get minus 11. And then you square it, you get 121. You divide it by the expected, and this is the final answer. So you would do this for each of the categories. And when you get all the answers, remember this E, kind of like an E, means sum of. We're going to add up the 0.2, the 0.3, 1.23, 1.49. And that is your chi-squared value. All right, so that is what you will do. Now, once you get this value, we're going to go to the chart I was showing you earlier. But before you go to the chart, you have what we call degree of freedom. Well, I told you about it earlier, right? So the degree of freedom. So we have 1, 2, 3, 4 categories. So I'm just going to call it n minus 1. So n is the amount of categories. And once you get, if you get a dihybrid cross, the number of category is going to be 4. So once it's dihybrid, you will have 4 categories because you will have 4 set of phenotypes. 4 minus 1, that will be equal to 3. So this is how you get your degree of freedom. Is that clear? All right. Oh, let me go back for the answer. So the answer was 3.23. So the first thing, what is the first thing that we should do now when we come to this table? Anybody? Which column should I pick?
Oh, look for the degree of freedom, which is 3.
Our degree of freedom.
Right, so 3, and then I go across to where?
Go across to the
It is 0.05.
Right. So this number here, right?
Yeah.
All right. So now what we're going to do is compare our answer, which was what, 3.23? I think it is 3 point something. Once your answer that you calculated is less than the critical value, you're going to accept your null hypothesis, which means that the difference between our observed and expected, it is purely due to chance. All right. So once
repeat what you said about once the calculated answer is less than the what?
the critical value. So this 7.82, that is our critical value. So you compare your chi-squared value that you calculated to the critical value. Once it is less, you accept the null hypothesis. So remember, this calculation is to determine if our you did your experiment, right? What you're trying to figure out, this difference, you expect to get 81 purple cut plants, right? And you got 70. Was it due to chance? Or was there something interfering with the process? So your null hypothesis is saying that any difference that you see is due to chance. So once it is due to chance, it is not significant. So when you do your calculation, you come to this table. So this is the table that you are going to use to tell you if the difference that you got, it is significant or not. So the critical value is 7.82. What we calculated was 3.23. The 3.23 is less than the 7.82. Therefore, we are not going to reject the null hypothesis. We are going to accept, which means that the difference is due to chance. Is that clear? So once it is less, it is due to chance. If it exceeds, yeah.
So the reason why that third Third one because the value we get at 3.23.
No, the degree of freedom. So
Oh.
to get the degree of freedom, it is the number of categories, so it's n minus 1, which is the number of categories, which is 4. So once you do a dihybrid cross, you're going to have 4 categories, and you take away 1 from it, which leaves you with 3. So so the degree of freedom is 3. So that is why you come to this here. And we are for biology, we are using 0.05. So look where the 0.05 and the degree of freedom meet. This value, yeah.
Them that give one table, like that's something that we say observed minus expected, and we put in those values.
No, I you that work it out.
We don't work that out.
Yeah, they can give about, more than likely they will want you to work it out.
Okay.
Or at least some of it, yeah. So ensure you remember the formula.
Sir, question.
Yeah.
Sir, what if they leave like the expected value come blank? How would you work that out? It's so nice. Sir, what if they left like the expected results column blank? How would you work it out?
Right, it will be blank. All right, so right, the expected, as I was telling you, is based on your not. So in the first part, let me go back to it's still on the board. Just a second. Right, so remember, when you cross 2 heterozygous offsprings, right, or a monohybrid cross, what is the expected phenotypic ratio? Right, that is where the answer comes from, you know. So when you do a monohybrid cross for 2 heterozygous offsprings, what is the expected phenotypic ratio?
3 to 1. 3 to 1.
Right. So once you do a heterozygous cross, it is 3 to 1. So this is what you expect. Now, what you're going to do is apply this ratio to a particular number you get. So I told you it was 100 flowers, right? So if you were doing the cross with, if you get 100 offsprings, of the 100, how many will be blue? Or how many?
75.
Right, so we expect 25 to be blue. And how much do we?
The rest 30 something.
25. Right. So the expected results is based on the type of cross we are doing. So they don't need to give you the expected results. You are supposed to know it. So you can work it out.
So we have to do the monohybrid cross and all of them stuff there.
Yeah, and if it's a dihybrid cross, you would have to do it.
Okay.
So, right. So for the dihybrid cross, right? If it's 2 heterozygous offsprings, instead of the 3 to 1, so 3 to 1 that's monohybrid. But the dihybrid is 2 traits. So the phenotypic ratio, let me just clear it.
Sir, before you talk about that, what do you say, like, however, if the calculated value is greater than the critical value, what will happen?
You reject the null hypothesis.
Okay.
Everybody familiar with Mendel experiment, right? And the green and the wrinkled pea plant? I'm assuming that, all right? So for a dihybrid cross, heterozygous, all right? So 2 heterozygous plant, you will get a phenotypic ratio of 9 to 3 to 3 to 1. If you're not sure, let me just remind you. So big R is round, small r is wrinkled. All right, that is in terms of the shape. In terms of the wrinkled and green, yeah. Big Y is for yellow and small y is for green. So in terms of the phenotype, the nine of them would be round and yellow. Round and yellow, it would be 9. Then if round and yellow, which other trait can you get?
Round and wrinkled.
All right. Round and wrinkled. 3. Which other trait I can get?
Yellow and green.
All right. Yellow and green. Which other one?
Wrinkled and green.
Sir, around and green, not yellow.
Thanks. Okay. Wrinkled and green is 1. What was the correction?
Round and green.
Round. Oh.
For the third one. No. For the one
The
below
third
that.
one, you have 2
Oh.
colors for the third one. You need to
Alright.
erase them.
No, but we can't have round and wrinkled because round and wrinkled a shape.
Sir,
So-
yeah, that one fixed too.
Right. Yes.
Yeah, round and green.
Right. It's supposed to be shape with color.
So
we have
round
round
and
and
yellow.
Oh,
yellow.
round and green and
Right.
yellow and wrinkled.
So round and green.
Green and yellow and wrinkled.
All right. All right. So round and yellow, that's 9. So no, it don't have to be people. I'm just going to tell you no. If you get a dihybrid cross, no matter which 2 traits that you are combining, right? The big R that is dominant, big Y that is dominant. The 2 dominant traits that will be the 9. All right. The 2 dominant traits that will make up the 9 in your 9 to 3 to 3 to 1 ratio. The homozygous recessive one. So look, wrinkled and green. Those are the 2 recessive ones, right? So the 2 recessive ones, where when they combine, you are going to get 1 in terms of the ratio. That's the 1. And then no, dominant with recessive, you get 3. Let me put that on the board quick. You can help you if it comes. So dominant and dominant, right? That is 9. Dominant and recessive, 3. Recessive and dominant, 3. Recessive and recessive, 1. All right, so this is how the phenotypic ratio will work for a dihybrid cross. Now, when you get, all right, so let's do it quickly. If you have 5 on, all right, let's say you have 375 pea plant, right? How much do you expect?
Excuse me, sir. So you're writing this now?
Say that again. If I'm?
Are you writing this now, whatever you're saying?
Yeah.
Because it's still on the null hypothesis page.
Yeah, I'm on the null hypothesis page. Hold on, all right. Tell me if.
Sir, we're not seeing what you're writing then.
Yeah, that's what I'm saying.
All right. I'm going to. I just erased the word hypothesis. Are you still seeing it?
No. Yeah. We're seeing it, sir.
All right. Let me stop share and click it back. Are you seeing it now?
Yes, sir.
All right. Just. Right. So in terms of doing this on the exam, the question will come, they will give you a cross to the right. Once you do the cross, you will get your expected phenotypic ratio. So this one. So what I'm saying now, in our example here, or in any example, once it's two heterozygous offsprings, your phenotypic ratio is 9 to 3 to 3 to 1. What I'm showing you, to save time on the exam, the two dominant traits, that will be 9. In our example, it is round and yellow pea plant. The dominant and recessive, meaning round and green, yellow and wrinkled. Dominant with recessive, that will be 3 and 3. And recessive with recessive, that will be 1. That is how the ratio works. So you won't need to be counting up in your table. Is that clear? You don't need to count up your table. So now, my question now, if you have 300 if you've got 375 pea plant, how much of them do you expect to be round and yellow? What would we do? How would we get the answer?
Sir, 57 of them. Wait.
Tell me the calculation you do.
Sir, you said 3. Wait, one the percentage?
375 plants. 375 pea plant. How much of them will be round and yellow? Right, in the interest of time, it's 9/16.
It would have been
So-
19% to be round and yellow.
So 9/16 times 375, how much I get?
Yes.
211.
How much?
Sir, 211.
And for the round and green, it would be 3/16 times 375. How much I get?
70.
All right. $70. And then it would be the same for the, all right. So this will get 211, 70, 70. That would mean this one is how much?
23.
23.
All right. So this is what we expect, right? I'm going to make up some numbers quickly. This is the made up number in block. 150. Somebody will work out observed minus expected squared quickly for me for this one. Divided by expected. All right, and tell me the answer. And next person, work out this one quickly. 150.
So the observed value would have been the one that will calculate, which is 211.
No, observed is in block. Expected is what you calculate.
Okay.
Yeah.
Sir, the first one is 61.
Give me a second. The first one I get 61. You divide it by the expected number. So you do
Oh no, I'm not do that yet.
So you must do 150 take away 211 squared
So I'm gonna get
divided by
17 point. Oh wait, I don't know. Wait.
each person just work out one of these for me.
So for the first one, we'll get 17.6.
All right, thank you.
Second one, I get 1.25. I'm not sure though.
For the second one, if you did
For the second one is 1.42.
1.42,
1.43.
for the third one,
No, sir, it's have to be 3 because the 8 come after the 2.
Sir, may I get 1.25 for the second one? And a 70 minus 80.
1.25.
no,
1.25.
80 minus 70, observed
Sir,
minus expected,
sir, you just say the observed one.
in black and the expected in green.
So number 3 is 0.
Right. And number 4,
Sir,
36,
and 17.57.
please repeat, how much?
117.57.
Anybody else? Just to double check.
Yes, sir, 117.57.
That sounds big, all right. 117.6, all right. All right, add them up now for me quickly. How much was it? 117 point, what you said, 57?
Yes, sir.
All right, so just add up the 3 of them now.
Sir, why you put 0? Oh, no bother.
All right.
$136.6.
Yes, sir.
All right. So our value is how much? 100. Sorry, repeat that again.
136.6.
36.6.
All right. So now, and our degree of freedom is how much?
3.
All right.
3.
Let's go to our chart now. Tell me what to do,
Look for your degree of freedom.
which is,
3.
all right. Oh, on the wrong chart. Right. Where is?
So
And then
because
go.
it's greater than it, it's greater than the 7.82. It
All right, so we
wrong.
locate the 0.05 and we locate the 3, right? And it meet here. So what would we accept the null hypothesis or would we reject it?
Sir, it reject it because the calculation
Reject
from
it.
It comes 7.82.
Yeah.
Right, it greater. So the difference between observed and expected, let me just go back to it now. Remember, our null hypothesis says that there's no significant difference between observed and expected. What is our chi-squared value telling us? Is it saying the difference is significant or not significant?
Not significant.
30 is significant.
Right. Remember, once it's over it, it is significant.
Sir, repeat the question.
The search I said significant.
So this value is 136, right? Our calculated answer.
Yeah.
Right. What is the critical value from the table? 7 point something, right?
Yes.
So once this value is greater than the critical value, we reject the null hypothesis. The difference we get, it is significant. We clear on that? The answers in green is what we expect to get. Ones in black are what we observed. When we did our calculation, our chi-squared value is 136. When we go onto the sheet, clearly, you find your degree of freedom, which is 3. You go across to 0.05, it meets at 7.82. 100 and whatever we just got is very, very larger than 7.82. Even if it was 7.83, once it is above it, what do? We reject the null hypothesis. The difference was not due to chance.
So, sir,
Mhm.
once the null hypothesis is rejected, that means that the significance is correct or something like that, whatever.
No, hold on. Before you go to the null hypothesis, this is what you are using to accept it or reject it. We calculated our value to be 136, right? Is bigger than 7.82. Once it is bigger, you reject your null hypothesis. That's simple. All right?
Yes,
Clear on
sir.
that? Okay. And what I'm saying, it was clearly, definitely not due to chance, because I mean, just make up some numbers, right? As you saw. So it was not due to chance, and me make it up. So that is why the difference, it was significant. Because look, if you expect this to be 23, I'm gonna put 75. That was some significant difference. Do you understand how it works?
Yeah, I understand now.
Right, it wasn't due to chance. I interfered with it, yeah. So if I did an actual experiment, even if there's a difference, it should be due to chance, all right? So this is, so what now? After you do the null hypothesis, you would come with an alternate, which is basically a rejection of whatever the null hypothesis is saying. So the null hypothesis is saying that there is no significant difference, but clearly there is a significant difference, right? So that is how we use this and apply it. All right, we have to move on. I'm going to stop sharing now. Well, I'm going to clear the screen.